Hi everyone, I'm Michael Roth. I'm from AMD, and I'm here to talk about accounting and page migration challenges in secure guests using FD-based private memory. So currently, user space uses the malloc, mmap, and related interfaces to allocate memory, and then it uses those virtual addresses to tell KVM what pages to use to back guest memory through the nested page table. And over the course of developing hypervisor support for confidential guests that support AMD's SEV-SNP technology and Intel's TDX technology, a need has arose for a different way to handle how we allocate and assign memory to guests. And essentially it boils down to using a file descriptor and an offset instead of the virtual addresses that are allocated to user space. And certain challenges arise in moving to that model, and that's sort of the focus of this presentation. So just to give you some more background on FD-based memory, the latest implementation of that is called guest memfd, or GMEM for short. You might also hear it referred to as unmapped private memory, or UPM. And it's essentially a way to back private guest memory with pages that can't be mapped or written to by user space. And there's some benefits to that, like it'll help protect against tampering of guest memory for user space. But since SEV-SNP and TDX both have hardware protections against that, that's not really the main driver of this. The main driver, or one of the big ones, is the fact that with TDX, if user space touches guest memory, that could cause a machine check. So there needs to be a way to prevent that from happening, and it's sort of tricky to prevent that if that guest memory is mapped into user space. Another benefit of this is that it provides a way to partition normal guest pages, the shared pages, from the pool of memory that's used for private guest pages. And that ends up being really useful both for TDX and SEV-SNP to avoid dealing with how we deal with issues like if the host is trying to access shared memory and the guest flips the state of that page to private while the host is trying to access it. We need ways to deal with that probably involve adding hooks and locks all over the place, but by having two separate pools of memory, when the host is accessing shared memory, that memory is always going to be shared. And when the guest switches to private memory, it's just going to start mapping memory from a different pool instead of changing the state of the memory that a host might be accessing. So let's look at how that's plumbed into KVM in a bit more detail here. This is how things work currently without GMEM. With normal guests and also with SEV and SEV-ES guests. So if you look on the right side here, we have a guest page table. It's got a GPA mapped into its page table for address 2000H, which is just normal shared memory, and then it's also got a private page at 3000H. And in both of those cases, if the guest tries to access that GPA, if it's not mapped into the guest's nested page table, then you'll get a nested page fault, and then the KVM MMU will then look at the mem slot and figure out what host virtual address is supposed to back that guest physical address. And then from that host virtual address, the KVM can then find the host physical address that corresponds to the page that should be mapped into the nested page table. Now with GMEM, there's now a notion of a private mem slot where for normal pages, things are still handled the same way, but for a private page, KVM now has this X array which tells the KVM MMU whether or not that page should be backed by private memory. And in cases where it should be backed by private memory, when we look up the host physical address of the page that we should map into the nested page table, instead of relying on the virtual addresses, we rely on the offset corresponding to that GMEM FD that user space passed to KVM. And as far as how we assign whether or not a guest should be, a guest page should be treated as private or shared. That could happen in a multitude of ways, but the main one is the guest can do what's called an explicit page state change, where it issues a request to the hypervisor to switch the state of the page from shared to private or private to shared. And with this GMEM model, what will happen in that case is that the hypervisor will get the request and forward it to user space in the form of a KVM exit, VMG exit, and then user space will then tell KVM that that GPA should now be treated as private using a new KVM set memory attributes ioctl. And there's another similar case for implicit conversions that basically happens the same way, so we don't need to go into too much detail there, but this is sort of how things are implemented with the current hypervisor patches for SEV-SNP support that have been posted upstream. Those are currently at version 9 right now. And things work pretty well with this model, but my colleague, Nikunj Didania, who couldn't be here due to some visa issues, he's been looking at some follow-on features for SEV-SNP hypervisor support, like page migration, which could be useful for a number of things. One of the more common ones is memory compaction. If you have a bunch of pages that are being used for private guest memory, because that's the main workload that the host is using, by not having support for page migration, you could potentially run into issues with fragmentation, and depending on how the guest access patterns are, and also things like NUMA rebalancing rely on page migration. So let's look at how we'd implement page migration with GMEM in the mix, and let's look at that in the context of memory compaction, which actually ends up being one of the easier scenarios to deal with, but still has some issues. So with memory compaction, there's a kcompact D kernel thread that periodically runs, and essentially it takes allocations that are scattered around the host physical address space and tries to migrate them to denser regions of memory so that we free up more of the host physical address space for larger allocations for things like DMA buffers and transparent huge pages. And one of the main interfaces, or the common interfaces that memory migration users will use, is the migrate pages interface. And just a few parameters there, but the more important ones are the from list, which is a list of pages that that we want to migrate, and a new page function, which is what allocates the target pages that we want to migrate to. And the migration in this case, or in most cases, will happen in two phases. There's a migrate folio unmap sequence, which will look at that page, and then it will look at the reverse map, which contains a list of all the VMAs across all the processes in the system, and determine which processes might have that page mapped into their virtual address space. And for each of those, it'll unmap that page from that process's page table, and then it will also issue MMU notifier events to let those processes know that that page is being migrated and that the process shouldn't attempt to, use it or map it until that notification sequence is completed. But one issue we run into here is that with GMEM, we never map that page into user space. So when we're trying to determine whether what processes we should send those MMU notifier events to, we don't see any VMA, so we don't send any notifier events to any processes. And that becomes an issue because the KVM MMU is one of the subscribers to MMU notifier events. And normally in response to something like this, it would unmap that page from the guest's nested page table so the guest wouldn't be trying to access it while that migration's happening. And that doesn't happen here, so that causes problems. And the next stage of migrating the page is when you do the actual copy of the source page to the target page, there's a migrate folio callback that's sort of registered by the GMEM instance, and that callback is what will actually handle copying the source page to the new destination page. And there's some generic migrate folio callbacks that various FD-based memory backends might be able to use, but in the case of confidential guests, we run into issues because generally you need hardware or firmware support to actually do that copy, or else the guest will treat that as its memory being tampered with. And that's not really an issue with GMEM specifically, but it's just something that GMEM needs to be able to handle if we're to support page migration. So one possible solution here is that the migrate folio callback, since it's aware of all these things, it can implement the hardware and firmware support that's needed to do the actual copy. And in terms of the MMU notifier events, because GMEM is actually specific to KVM, it's not going to be used anywhere outside of KVM, it's not such a bad thing to have that migrate folio callback also sort of manually issue those KVM MMU invalidations to make sure that those pages get unmapped from the guest's nested page table. And so with those things in place, things sort of work out for a compaction, but as we start looking at other use cases, we start running into other issues that sort of result from the fact that this memory doesn't have any associated VMAs with it. So let's start taking a look at that. So in general, memory that's allocated by GMEM is basically accounted by the host as page cache allocations. It's not accounted to any specific process, and that's going to end up causing problems if you're trying to set process limits on how much memory a particular process can use, or C group limits and things like that. Because it's just sort of treated as page cache, those things aren't really taken into account the way you'd expect normally. So one example here is we have an SNP guest that has 40 gigabytes of memory that through NUMA CTL has been instructed to allocate evenly between NUMA nodes 2 and 3. And in this case, SMP guest isn't using lazy acceptance or anything like that, so at boot time it's actually going to touch all 40 gigs of that memory. But if you look at the resident set size of the QMU process that's running the guest, it's only 85 megabytes. So if you're trying to place any limits on memory usage, the normal mechanisms aren't really going to work out here. And also, if you look at things like NumaStat, you're not going to see that those pages were actually allocated from node 2 and 3 based on the NUMA policy, but they're not going to get accounted to the QMU process, even though if you look at the overall file pages usage, you do see that they are coming from nodes 2 and 3. And if you dig a little bit deeper into why that might be and start looking at things like proc files, if you look at NUMA maps, there's 4 files listed here, and they have useful information about like how many pages are allocated to a particular node. But in the current implementation of GMEM, for every one of those FD-shared files, there's a corresponding FD-private file that's not showing up here. And the main reason that it's not showing up is because the way these things are listed out is basically by walking that reverse map, looking at all the VMAs of that process, and then sort of listing them out here. But because there's no VMA, we don't see that. So it seems like a lot of these issues sort of stem from not having a VMA associated with the memory that's being allocated through the GMEM file descriptor. So maybe one of the simplest solutions is just to kind of give the kernel what it wants and allocate some sort of shadow VMA or invisible VMA, so that all of this accounting stuff just sort of magically starts working because there's now a VMA that's tracking that. But it ends up not really being that easy. You obviously needs to take care that those mappings don't actually result in that memory being mapped into the process's page table, or else you'll run into the issues that GMEM specifically is trying to avoid. And also, just having VMAs isn't enough, because a lot of that accounting is going to happen through at the time that the page is actually faulted in and touched, not just when that VMA is created. And because there's no normal page fault mechanism where that accounting would normally happen, we sort of need to kind of duplicate that accounting somewhere in KVM when we're actually pulling pages out of that GMEM backend to back the guest memory. And there may be other solutions that could be pursued, but nothing that's clearly or necessarily better. And since I actually thought I wouldn't have time to cover it, there's another issue here, which is with NUMA bindings. I had mentioned, I had the example earlier where we used NUMA CTL to set what nodes the guest memory should come from, and that actually worked out pretty well, but that doesn't help too much in the case of QEMU, because QEMU tends to use mbind to handle setting NUMA policies, so that it could do things like have two virtual NUMA nodes and map those to the actual physical, or pin those to the actual physical NUMA nodes on the host to sort of mimic the host NUMA topology. And NUMA CTL doesn't really help with that sort of thing. So underneath the covers, a lot of the QEMU interfaces to handle NUMA bindings rely on mbind. But the issue with mbind is that it takes a virtual address, and because we don't have a virtual address for that private memory, we can't use mbind. So I think there's been some discussions upstream about potentially introducing a new fbind ioctl that can do what mbind does, but do it given a file descriptor and an offset. There's other potential ways that we could potentially approach it. One of them is that, because there's generally going to be a shared memory allocation for a particular range of memory that sort of corresponds to that physical allocation, that private allocation of memory, and it's really just that X array that's telling the KVM MMU where to grab each particular page from the shared pool versus the private pool. So maybe it makes sense to sort of just mirror the NUMA policies that are set on that shared pool to the private pool, but in some cases maybe KVM's not aware of how those policies are being set on that shared pool and doesn't necessarily have the insight or get called at the appropriate times to make something like that happen. So that's another area that is worth looking into. But in summary, GMEM provides some very critical infrastructure that's needed to finally enable confidential computing in KVM for things like SEV-SNP and Intel TDX. But when we start looking at things like page migration and memory accounting, there's some gaps that remain there. And the current implementation for users that really put security above and beyond all these other things is probably sufficient, but we will probably need to address some of these other gaps, and some of the solutions could potentially be fairly involved and complex, so we could definitely use some help from the community and any of the memory experts to make sure that we can find the right solutions to some of these issues. And I think that's it. If there's any questions. Sure.
So the kind of changes you're talking about, like potentially representing the range of VMA as virtual addresses, they seem quite fundamental changes to the current proposal of FD offset. How much of this do you think we can realistically retrofit into the current proposal for faultless offset, and how much do you think we should actually hold off the current approach, which has been going on for too long already?
Yeah, I mean, I would certainly prefer sort of a staged approach if possible. There are areas in the kernel where will allocate things like pseudo VMAs to help with the accounting. So it's not like this is, you know, the first time anybody's looked at taking that sort of approach. So it, you know, it's possible that we could just sort of work it in the next version. And maybe for some of the memory accounting stuff, you don't even really need to address the VMA thing. Maybe it's okay that some stuff like numastat and some files don't show up in proc, but maybe as long as we at least do stuff like account the memory that's being used by GMEM to the guest's resident set size, maybe some of the more important policies will at least be honored. So there might be, you know, smaller, I guess, you know, fixes that could be made to enable, you know, some of that other stuff. Sure. Anyone else?
I was wondering whether it would be possible to, instead of unmapping this memory, just making it inaccessible by, for example, setting a reserve bit in the page table instead of completely unmapping the memory. That would allow to keep the DMAs around and would allow other code to, with the migration decisions, they can usually ignore the reserve bit set. So, could that be a possible solution? What do you think?
Yeah, I mean that's sort of what I was thinking of with creating those pseudo VMAs. If you took it to the extent that you actually mapped it into the process page table so that basically everything works the same way it does with normal memory, that would solve a lot of solutions. But then you need to make sure that there's a way to map it into the processes page table in a way where if that user space process try to access that memory, all the same protections still remain in place, where you can't write to that memory, and there could be potential complications if there's restrictions on whether a THP mapping can overlap with a private mapping, where even if you don't actually write to a particular page, maybe the fact that you're writing to a huge page that overlaps with a page of that sort, you know, there could be some issues that need to be.
Yeah, so THP probably needs interaction with the guest because it just needs to know which pages are split up and where it has to use 4K and German mappings, right? So, but I think everything else can probably work with when the DMA is around and just it's just inaccessible because the result is set and decide that everything is still in place as it would be with normal memory.
Yeah, that would be my hope, because it seems like it would solve a lot of problems if it could be done that way. Yeah. Question in the back?
I have a question from Google. So one issue that we were having was, I think, one is also push page and push level and so on. Because when we come to page accounting, and that's also relates to how we're going to allocate those shape page code. If the drive page are coming from push page, right? Then it's a challenge, especially coming from a push level S page, you can actually break down time. Now you might need to allocate additional shape memory, which end up causing double applications, and there's issues with accounting those additional memory and how can we manage that. So I don't have a solution. I'm just sharing that is not only but also supporting the push page, those are other challenges we need to think about. Coming to the having a VMA mapping, I think that has been originally proposed before the boot camp. But there were some other challenges, like because overloading the, I think there was some suggestion about using poison bit or something to prevent having those private pages in the same page table mapping. Then there were some other challenges and direction. Also, it's just using the listed active. So we might still discuss them, but there were a lot of ideas, and I don't think there's a easy solution, but each page is also
Okay. Yeah, I wasn't aware of any previous discussions around that, but maybe it makes sense to revisit some of those things in the context of GMEM. All right, well, if there's no more questions, then I guess that's it. Thank you, everyone.